All right, this video is for calculus, infinite series unit. And we're going to talk about the last part in the first half of the unit, which is whenever you have an alternating series, if you don't use the entire series, but you stop after a certain number of terms, there's a difference between that sum and the actual sum for the full series. And that difference is called the remainder or the error. So this is specific to working with the error or the remainder for alternating series. All right, let's go ahead and get started here. Whenever you have now you have to have an alternating series. This applies only to alternating series, and it has to be a converging series. So if the series diverges, this doesn't work. But if that's true, you have a convergent alternating series, then you can approximate the sum that the actual series sums to, the actual sum, by only using some of the terms. Okay, to kind of build up to that. Let's take this series right here. So we have an alternating series. I can tell this is an alternating series because of the this term right here. This is an alternating series. And if I were to write out the terms of the series, you can either just manually plug things in, or let me remind you that you can use a calculator for this. If you treat the series generating rule as a function, you could put a calculator into regular mode here, graph it, graph the function, -1 to the, let's see, up arrow. I'm going to use the variable key instead of the n there, +1. And then that's going to be divided by variable key squared. So you could enter the generating rule as if it was a function. Then you could, for example, go to a table setup, have it start at n equals 1 and go up automatically by 1, and look at the table view and see the terms. So the first term of this series is a 1, the second term is -0.25, the third term is 0.11, the fourth term is -0.06. So that's what I've got written here. This is the individual values of the term, which we would label A1, A2, and so on. Just highlight that the values of the terms are A1 is 1, A2 is 2, A3 is -0.25, and A3 is 0.111, and so on. Okay. So that's how the series of the terms proceeds, the sequence that makes up the terms. And we can see that these are approaching, looks like 0, okay? And then when I'm actually talking about the sum, right, we're talking about infinite series, which means we're summing these up. That means we could do a sum for that entire series. Let me go back to the calculator here and use a different part of the calculator. If you go to math, and then scroll down or up to the summation, you can do a summation from x equals 1 to some number. So let's say, for example, just 1. If I just go from 1 to 1, I'm only getting the first term. And this, I'm going to put the generating rule in here again, -1 to the up arrow x plus 1. And then that's divided by x squared. Okay. So now if I do this, I'm doing a series from n equals 1 to 1. So that's just the first term, right? And I get the sum 1, okay? If instead I want to take that same series, but I want to get the first two terms, that's a summation from n equals 1 to n equals 2. So that's summing up two terms, and they sum up to 0.75, right? Or if I wanted to go to the fourth term, let's say, so summing up the terms 1, 2, 3, and 4, that sums to 0.7986. So that's what I've got written down here. I've got the sums themselves. So this 1 is just this 1, right? This 0.75 is 1 plus -0.25, right? And the symbol for this is the partial sum with one term included, the partial sum with two terms included. Right, S3 would be you add this term and this term and this term together, so you have three terms, and that sums up to 0.8611. Then if I add on a fourth term, right, that's called S4. So this is called a partial sum. We're not doing the entire summation. We're just doing, some of the terms. Okay. So what this section is about is, if I'm just working with the terms themselves, the series terms, A1, A2, A3, A4, and I plotted the term values, so A to the n versus n, the terms are jumping around from 1 here, the -0.25, 0.111 to negative 0.0625 and so on, right? So they're alternating around, getting closer and closer to zero. The partial series sums, so if I include one term, this sums to 1. Then when I add these two together, I have a partial sum of 0.75. So this starts at 1, partial sum S2, so this is S1. This is S2, which is at 0.75. S3 is when you sum up 3 terms, and that sums to 0.866, so this is S3. S4 is if you sum up the first 4 terms, and so on. And if you plot what the partial sum is doing, it's oscillating around a value 2. That value that it's eventually going to approach, if you go all the way to an infinite number of terms, is the true value of this sum, right? What does this sum actually equal? And the symbol for that would simply be S. It's the sum itself, okay? By deciding to stop early with only some terms, we're truncating the series after the first term or after the second term or after the third term. Okay, so now that we've got some terminology established, let's take a look at if I just decide to stop. So let's say that I've got a series and I write out some terms. So the first term is 1, the second term is negative 0.25, and 0.11, negative 0.0625, and I keep going. If I decide to cut this off right here, so let's say I only want to use the first 4 terms. The word for that is truncating the series. If we truncate the series or cut it off after the first 4 terms, that sum there would be called S4, the partial sum with 4 terms included. And that is some value, right? That's this particular value right here, because I've only got the first 4 terms included, right? But there's an actual value, which is the true sum. And that difference right there, that difference we call the error or the remainder between the truncated sum and the full sum. Okay, so now that we've got all that terminology, let me show you the theorem that says this. You can say something about this sum. If you go far enough out in the terms and the series is converging, you can get as close as you wish to the actual sum. The more terms you include, the closer your approximate sum is equal to the actual sum. Right? The difference is called the remainder, or it can be called the error. And it's just the difference between the actual sum and the partially truncated sum with n terms included. Usually we'll use the symbol R for the remainder. Okay, so here's the theorem. If a converging alternating series satisfies the condition that it's decreasing, which has to be true for it to be converging, then the absolute value of the remainder, or the error, is less than or equal to the first neglected term. So the first term you don't include. All right. So what that's saying is, going back to this picture, right? If you look at this error here, this error between the actual sum, the sum up to this point, and whatever the true sum is, you would just figure out what the very next term is. This is called the first neglected term. Whatever that term is, right? The difference between this and the actual sum is never more than that first neglected term. Okay, we're not going to try to prove that theorem. It may be proved in the textbook, but we're just going to show how we can use that theorem. All right, so let's say we have a question like this. Approximate the sum of the series by its first 6 terms, okay? Well, what I would do is write out the first 6 terms. So if you just plug these numbers in here, and I'm going to actually do this by hand real quick, although you could use a calculator if you prefer. This is an alternating series. It starts with a 1 here. So this is negative 1 squared, so it starts with a positive term. The first term is, let's see, 1 over 1 factorial. The next term would be negative 1 over 2 factorial. Then we have positive 1 over 3 factorial, negative 1 over 4 factorial, positive 1 over 5 factorial, negative 1 over 6 factorial, positive 1 over 7 factorial, and this continues indefinitely. In fact, if you're writing this, you should do a ... out here. Okay, so if we're approximating this sum by the first 6 terms, 1, 2, 3, 4, 5, 6, that means we're truncating this right here, okay? In order to get that, I mean, I could kind of calculate this all by hand, but now I am going to use a calculator real quick just to do that. I'm going to put in, actually I'm going to do this. I'm going to enter it as a function here. So this is negative 1 to the n plus 1. But for this part out here, I'm going to write 1 over n This is going to be n factorial. So let me get rid of the rest of this here. It's going to be divided by that, and then the factorial symbol is under the probability menu. Okay, so I've got my rule in here for y1 for the rule. So if I want to do a summation, right, I can go to math summation and say, oops, I got to not do that inside the graph. So let me get rid of that. Go back to the command line and then do math summation. I'm going to go from x equals 1 to just the first 6 terms, so 1 to 6. Rather than retype this, that's under variables, y variables, function variables, y1, because I already have the rule in there. And that sum turns out to be 0.6319444. Right, so this sum right here, which we would label S6, because it's the partial sum, is, let me look at it again, 0.6319. 0.63194444. Okay? And usually, even though we normally would round to 3 decimal places, because we're talking about small errors here, I usually write the entire amount. Okay, so we've literally approximated the sum of the series with a partial. This is approximately the value. But the true value, since we're trying to approximate the actual sum, is somewhere between here with an error. Right? That means that there's going to be some error to this. So I could take my x6 number, and then I could go back here for a second. The actual sum s is going to be somewhere between s6 plus the error or s6 minus the error. Technically, it's equal. So the real sum is somewhere between that and the error. The question is, how big is the error? Well, the theory says that the error is less than or equal to the first neglected term. So the first neglected term is this, 1 over 1/7. So this error, or sorry, is 1 over 7 factorial. So what is that number? Well, let me just write it like this. The actual sum is somewhere between this 0.6319444 plus that error of 1 over 7 factorial, or that 0.6319444 minus that error. If you calculate those out in decimal, this one turns out to be 0.631746 and 0.6324143. So I can approximate it and get the approximate truncated value, but I know that the true sum of this series is somewhere between 0.631746 and 0.632143. That's actually what this question is asking me to do, to use this theorem about the fact that the error is no more than the first term you didn't include, above or below the actual amount that you found from the truncated sum. Right, so that's the first example, and that's how we would do a problem that is worded that way. Okay, let's take a look at another example. Determine the number of terms required to approximate the sum of a series with an error of less than 0.001. Right? Well, what we can do is this. I would do it this way. I would say, let's include, I'm going to use a capital N for how many terms I'm including. So let's include capital N terms. And that means that the theorem says the absolute value of the error is less than or equal to the first neglected term. I actually would write that to telegraph to the scorers on the AP test that you know the rule. And so that means that this is less than or equal to the absolute value of the n+1 term. So I'm going to take this rule. Since it's absolute value, I don't have to bother with this part. But it's 1 over capital N plus 1 to the 4th power. Right, so that error is definitely going to be less than 1 over n plus 1 to the 4th. Now, if I want this to be an error of less than 0.001, then that means that I've got a little thing I can solve here. 1 over n plus 1 to the 4th has to be less than 0.001. Okay, if I flip both of these upside down, right, then this becomes n plus 1 to the 4th over 1 is less than 1 over 0.001 is 1,000. And so that means that I could maybe take the 4th root of both sides, and you would get n plus 1, therefore is less than the 4th root of 1,000. And then that means that n would be less than the 4th root of 1,000 minus 1. Now at this stage, we can go ahead and plug that in a calculator. So let's do that. If I just took 1,000, to do the 4th root, I'm just going to go up arrow to the 1/4 power. And then I'm going to subtract 1. And that is 4.62. So that is 4.623 terms. But since I can't include a partial term, I'm always going to round that up and say that I have to include 5 terms. If I include 5 terms in the series, then the error will be less than 0.001. Okay, so that's how it would show work if I was asked a question in this form. Okay, I've got one last example. I think this is it. How many terms do we need to approximate an error of this one to less than 0.002? This illustrates something else that can happen. So same kind of setup as before. We could start by saying we know that the absolute value of the error is less than or equal to the first neglected term, which is, let's see, the error is less than, let's see, if I'm going to include n terms, then this is going to be the n plus 1 term. So that's going to be n plus 1 over 4 to the n plus 1. Okay, and then that has to be less than 0.002. All right, so it would be nice if I could solve this by saying, okay, n plus 1 over 4 to the n plus 1 is less than 0.002. Now on this last one, it was easy to do some algebra manipulations to actually solve that for n. And in this case, it's not as easy, right? We've got a mixture of kind of a linear function and an exponential function, so not as easy. So in this case, what I do is I basically switch to guess and check. Right, what I'm going to do is I'm just going to pick some values for the terms. So what I'm going to do is I'm just going to write out the terms of the series. Okay, so let's write some of these terms out. Often this in the AP exam is in the no calculator part of the test. So let me show you what you could do with no calculator, although I think we probably will have to resort to a calculator. So let's just write out the terms. The sum from n equals 1 to infinity of negative 1 to the n, n over 4 to the n. The first term is going to be negative, and it's going to be 1 over 4 to the first power. All right, the second term is going to be positive, and it's going to be 2 over 4 squared, which is 16. And then we've got negative 3 over 4 cubed, which is 16 times another 4 is 64. And then the next term will be 4 over that. Now this is where I would need a calculator. 64, so 4 to the 4th power is going to be 256. So I'm just going to write some terms out here. 5 over, if I take that number times 4 again, 1024. Let's do another one, 6 over, multiply by the 4 again on the bottom, 4096. 7 over times 4, this is going to be 16,384, and so on. So this continues, right? And then what we're going to have to do is figure out what these numbers are in decimal to see when is the first neglected term going below this goal of 0.02. So I'm going to write what these are in decimal, just ignoring the signs. This is 0.25. Actually, let me change colors. This is 0.25. 2 out of 16 in decimal is 0.125. We're still not below this 0.002. 3 divided by 64 is 0.0469. still not below 0.02. 4 divided by 256 is 0.0156, still not below. 5 divided by 1024 is 0.004, still not below. 6 divided by 4096 is I'm going to change colors here. This is 0.0014. Now, this number here is finally below our value of 0.02. So this can be the first neglected term. Neglected term, which means we can truncate right there and include 1, 2, 3, 4, 5. So we need 5 terms so that the first neglected term goes below our goal of 0.002. So I included this example to say, sometimes you luck out and you get something where you can actually use algebra to solve for the number of terms. But if not, you can just switch to kind of guess and check. You just write out the terms, you figure out what they are in decimal, and you just truncate the term when the next term goes below the goal. And that's it. That's the error or the remainder for alternating series. All right.